So in the last class we proved Savage's theorem. So n space class is really simulable by efficient space. S becomes S square. In particular, NP space is equal to P space. So non-determinism doesn't really help if you are in a class as big as P space or bigger. And yeah, so we also looked at this configurations tree, and this will give us a new way to define small complexity classes like NL. So this configuration tree is you start with the start configuration and then you proceed downwards from the root of this tree. In each step, obviously, you have two possible configurations because of non-determinism. So I left as an exercise to compute the size of this configuration tree and to actually check or test reachability in 2 raised to s time and that much of space. Okay. What we have shown above is actually just S space. In S space, we can solve reachability. Sorry, S square space, we can solve reachability. But for S square space, how much will be the time? So time in the worst case can be 2 raised to S square, right? So if you want to reduce the time by increasing the space, that question is the space-time trade-off question for the reachability problem in directed graphs, because this graph is directed. So let us look at NL now. I don't remember whether we defined it. Let's define it here. So NL is the class n space log n. Okay, it's non-deterministic space log n. So which you know is contained in space log square n. That much we know, but we are actually more interested in comparing it with space log n. Okay, so how does n space compare with space log n without this blow up? Is this blow up necessary? That's the question we are interested in. Also, another thing that you can see is that log space is in NL. That's immediate. I mean, that is by definition, because space log n is obviously in n space log n, and this NL is actually in polynomial time. Why? Because it's simply a question of reachability, right? Or maybe I should not. I should put it differently. So, what is the number of configurations? So, number of configurations is 2 raised to big O of log n, which is n raised to constant. So, number of configurations is only polynomial, right? So, whatever you can do in polynomial time. So, this means poly n time. So, it's solvable in polynomial time. So, NL is in P. This also follows from the relationship between space and time, right? We had shown at some point that space S translates to 2 raised to s time. So, this is a similar argument. So, NL is somewhere between log space and polynomial time, and probably much closer to log space than polynomial time, but we don't know by how much. So, for let's now study a problem that is the hardest in NL. So, for a meaningful notion of hardness, in NL, we need log space reductions and not polynomial time reductions. Right? Why not polynomial time reductions? Because polynomial time is bigger than NL. So, obviously, every problem in NL you can reduce to any other problem in NL by polynomial time, because everything you can solve independently in polynomial time. So, to have a notion of hardness here which is more meaningful, that is within the world of NL, you have to actually restrict your reductions, and we will restrict them to all the way to log space. Right? Log space is smaller than, it is contained in NL. So, that will be a more useful notion of reduction, and based on that, let us do the definition. So, call a function strings to strings implicitly L computable if, so intuitively you want to call a function, call f implicitly L computable if the ith bit is in log space, right. So, that is what we will say. If the language LF, which is input string x ith location, is 1, and the language LF prime which is again input string x ith location, the length of fx is at least I. So, LF prime is checking the length, and LF is checking what is the kind of, think of the last bit. Okay, so, if because in the case when the length is less than I, then there is no point asking for ith bit. So, you can think of this as checking the length whether it is at least I, and then asking for ith bit. Both these problems are solvable in log space. Okay, when this happens, then we say that f is implicitly L computable, because every bit can be computed in log space. Okay, so, this is something very natural, nothing surprising here, and we call, now we define reduction. So, we call E reduces in log space to B if there exists an implicitly L computable f such that for all input strings x is in A if and only if f of x is in B. Right. So, this is expected. If you recall KARP reduction, this is exactly the definition. A reduces to B if yes string maps to a yes string, and vice versa. Image is yes if and only if the pre-image is yes. Except that f is now very restricted, f has to be an implicitly L computable function. And finally, we call B NL complete if B is in NL and for all A in NL, A reduces to B. Okay, so B will be called NL complete if B is in NL and every problem in NL reduces to B by an implicitly L computable. I mean, there is a log space reduction basically from A to B. Okay, so let's now discuss some quick properties that we can deduce. So A reduces to B reduces to C, log space reductions, then A reduces to C. Right, this seems obvious from the face of it, but it's not completely trivial because remember that its log space reduction is only implicitly L computable. So, and it's a very weak kind of reduction, it's a very restricted reduction. So, you x in A will have to be mapped to first f of x, f1x in B and then f2, f1 x in C. But you don't have enough work tape space to store the whole output, right? So, you have to do this bit by bit, that's the problem. And second property is if A reduces to B and B is in log space, then A is also in log space. Okay, let's prove the first one. As I said, it's not completely trivial. So, let FG be implicitly L computable functions. Then the claim is that G composed with F is also implicitly L computable. Okay, why is that? Why is the composition also implicitly L computable? So, the proof for this is so while computing f of x, or I should say while computing g of f of x, so while computing g of y, if you need yi, whenever you need yi, do the f of x computation. Okay, so you think of just computing a bit of g of y, and while computing the jth bit of g of y, whenever you need some bit of y, let us say yi, then you do the f of x computation for finding that bit. Okay. Now, each of these computations, they only require log space, order log n space. So, order log n plus order log n is order log n. So, this means that space needed Okay, so that's the final space. So you can actually compute jth bit of the composition also in log space. That's the major idea here. So once you have done composition, then you have reduced A to C. So this implies that A also reduces to C. Right, and what about the second one? So in the second one, B is in log space, right? So same composition rule tells you that you can actually solve A also in log space. The composition rule implies that A is in log space. Because B is computable, so you will reduce A to B and then use this subroutine to actually solve A. Right. So so log space is a very nice reduction idea. Right. Previously we had used polynomial time reduction. Now log space will be a very good substitute for these small classes like NL. So let us now see let's see an NL complete problem now. So this will be, so remember the way we motivated NL was via reachability in a tree, right? So reachability is a good candidate. So let's define path to be graph and two vertices ST such that S to T there is a path. So this should be called actually directed path, but we'll continue with this name. So path is given a directed graph and two vertices, source target, whether there is a directed path. Okay, these are the yes instances. So obviously this is I mean practically it's a very simple problem. You can actually solve path in linear time. Right. So time wise it's quite easy. But suppose we want to optimize space as much as possible. So is this linear space the best, or is there a better space complexity for this problem? And that is what we will answer, or that is what actually we will formalize. So first we show that path is in NL. Okay, so actually with non-deterministic guesses you can solve it in log space. This directed reachability problem, path problem. So why is that? Well, because you can just guess the path from S to T. Right, you keep guessing and you will only need to guess log bits for one vertex. And with every guess you will move to a neighbor and maybe you will end up in T starting from S. So let GST be an input instance each vertex can be identified by in log G space right. There are vertices many, I mean size of G many vertices are there, and so log of that is the amount you need. So I mean technically it's the ceiling of this, but this we generally ignore because of the asymptotics. But ceiling of this many bits will suffice to index any vertex. So you just have to guess for a neighbor. To guess a neighbor, you just need this much of non-determinism. Then from a vertex you can move to the neighbor. So this means that NDTM M that simulates a walk in G with origin S and accepts on reaching T. So this NDTM M, right, which just keeps guessing neighbors, neighbor of S, then neighbor of S, and so on, ending up in T, accepting. So this has space complexity big O of log n, right, which immediately implies that path is in NL. So we have shown that directed reachability problem called path is in NL. So the optimized space will be actually log. If we can remove the non-determinism, then the correct space is log, right, which is an exponential improvement if we can do it. So can we do it? That's the question. So can this be really made log n space? So let me instead say space log n or log space. Right, so then it will be a practical algorithm which will only require log space. Time will remain polynomial time, but space will drastically improve. So is this possible? So keeping this in mind, this motivation in mind, we will show that this question really depends on NL equal to L question. So we show that for every language A in NL, actually A reduces to path. Okay, so NL actually path is NL complete. So if you can solve path in log space, then you can solve NL in L. NL will become equal to L. Right, so depending on whether or not you believe in the algorithm, log space algorithm for directed reachability, you also have to believe NL equal to L or not. So how do we do this reduction? So this will really go via the configuration tree. Okay. So let M be NDTM. Deciding A in space d log n, where d is a constant. So let us now on an input GST, g comma s comma t, or input x, actually input x for the problem A, let's convert x into a g comma s comma t, a path instance based on the configurations of M. So consider an F that maps input x of A to f of x g comma s comma t path instance, where G is the configuration graph of Mx. Okay, so we are now looking at this configuration graph, or also configuration tree, as we saw before. So what are the details of that? So vertices of G are all the configurations of Mx. Right. So M of x, for example, starts with a start configuration, then moves to 2 options, then each of those move to 2 more options, and so on, end up in either accept or reject configuration, depending on whether x is in A or not. So that configuration tree vertices become the vertices of G. Second is S and T are the start and accept configurations respectively. And when is there an edge between 2 vertices? So an edge C to C prime is there in the edge set of G. That is the vertex set, and there is an edge C comma C prime of basically C and C prime are configurations in the edge set if and only if C to C prime is a valid transition step. Of Mx. It's single transition, not path. So there is an edge C to C prime if and only if C to configuration C prime is allowed by the transition function of M on input x. So that's the complete description of this directed graph. It's obviously directed because C to C prime being an edge doesn't mean that C prime to C there is an edge. Right? The computation, the transitions may not be reversible, and you can conclude immediately that X is in A if and only if this G comma S comma T instance is in path. Right? X is in A means that there will be an accepting path, which is what G comma S comma T in path says. So this is clear. The other important thing is how fast can you compute F? So that's the claim, that F is implicitly L computable. So why is that? Why is F implicitly L computable? So this idea is that first the list of vertices is, they are L computable. So vertices, so the configurations basically, right? List of configurations you can assume in some order, and when you want the ith bit in a configuration, in that order you can just assume the definition of a configuration for the Turing machine M of X. Right. So in the configuration you have the state, the tape information and all that. So those things can be just encoded properly. So use order them and use the definition of configuration. Okay, just by this you will see, you will be able to implicitly L compute the vertices. So indexing a configuration will be easy because the number of configurations is polynomial, right? So that's important. And then given C comma C prime, testing whether C to C prime is a transition. Whether this is a transition of Mx requires linear space, right? So C is the configuration space is basically dependent on the workspace, which is log. So this whole thing is doable in log space. You just have to compare the entries in basically one position to see whether C to C prime is valid, right? So that is again log n space. Okay.